Hi guys, let's see some properties of equipotential surface. Suppose if I take a positive test charge, so this is right now right at here. So this is, I'll consider a positive test charge, and these bubbles are the equipotential surfaces for this positive charge. So how it is? Suppose if I draw on the surface, this is at a distance r, so the potential at a point, if I take that one, so this can write k q upon r. Similarly, on the same surface on another point, if I can draw, so this is at a distance r, the potential at point b, if I can take that as, that is also k capital Q upon r. Therefore potential at a equal to potential at b. Now if you can take any point on the surface, so that on that point also having the same potential, so that's why this surface we termed as equipotential surface. Now this we can call as equipotential surface. Okay, now let's see certain properties for this equipotential surface. So first property, suppose if you take electric field lines for this positive charge, suppose if I draw the electric field lines from the positive charge, so these are the white lines, they are representing the electric field lines. Now if you write a property, first one, the electric field lines are perpendicular to equipotential surface. Yeah, they are the perpendicular to equipotential surface because the electric field lines is piercing the equipotential surface. So if you can take the area of that particular surface and electric field lines, so they both are the same at any location. So the first point, the electric field lines are perpendicular to the equipotential surface. So that is the first point. And the second point, if you can take, so equipotential surfaces, so here the E, you just try to read as equipotential, not the electric potential. So earlier I used to mention that E as electric potential. Now in this case I will take that as equipotential surface. Equipotential surface never interact. Yeah, this is a property because we are selecting equipotential surface at a location. So that distance is different from the different locations from the source charge. So equipotential surface, they never interact each other. And the third and very important point, the work done moving a test charge over the equipotential surface is equal to 0. Suppose if I take a test charge at here, so that is at a point A, so I am having a small test charge and I want to move the test charge from A to location B, so that is also at the same distance. So this is the location B, so they both are having equal distance. Now I am moving the test charge over this location on the equipotential surface. So I am moving test charge over the equipotential surface, not across the equipotential surface. Since potential at point A equal to, we can write that potential at point A equal to k q upon r. and potential at point B is also V suffix B equal to K capital Q upon R. According to definition of the potential difference and work, so we can write that relation. Since potential difference VB minus VA equal to work done per test charge, here the little q is my test charge. So this is the definition of potential difference. We define potential difference as work done per test charge. Now here you can substitute the values of the VB. So at the VB its the value is KQ upon small r. At the VA also K same value KQ upon small r, which equal to work done per test charge. So on this left side will become equal to 0. So the work done per test charge. So and therefore work done equal to 0. So it means there is no requirement of work when you are moving a test charge over the equipotential surface. So that is a very important point. If I write mention it here, no work is done in moving a test charge over an equipotential surface. So there is no requirement of work if you are moving a test charge over the equipotential surface. So this point is very important point under the properties of equipotential surface. But when you are moving across means, suppose if I take a point at C. So this is a point at C which is at a distance of R2. So I hope this is not visible. So this is a point C location which is at a distance of capital R. Now if you can write the potential at C, so VC equal to K capital Q by upon capital R. Now if you are moving a test charge from VC to VB, so you are moving across one equipotential surface to another equipotential surface. So in that case, the potential difference is different, so work done will not be 0. So if we are moving across equipotential surface, work done is not equal to 0. So try to get the meaning of work done equal to 0 over the equipotential surface, and work done is not equal to 0 when we are moving across. So when we are coming from high point to low point or one point to another point, so the work done not equal to 0. So these are the properties of equipotential surface. So I would like to relation between electric field and equipotential surface. This is a very important relation between the electric field and electric potential. So if we are having a common formula between electric field and electric potential, it's very easy to understand mathematically, and it's very helpful to solve the problems. So for that, as usual, let me consider write it here, a positive source charge. And now if I take a point at a distance, so this is a point A. Now if you can write the potential at point A, VA equal to, let it potential as V itself. Now I will take one more equipotential surface. So this is another equipotential surface which is at point B. Now the potential at point B I can write here as VB equal to, so V plus dV. So the dV is a small extra potential because the B point is very close to source charge, automatically potential value will increases. Now if you take, I am moving a test charge from point A to B. So if I am trying to move a test charge from point A to B, trying to moving a test charge, which is Q naught. So to move a test charge across the potentials, so in that case I need to do work. So according to definition of the work, so potential difference equal to work done upon test charge. So here the potential difference, if I can mention potential difference, VB minus VA equal to, here I can write the work done at here. The test charge I will take as Q naught. So substitute the values of the potential difference VB, we have at here V plus dV minus potential at A which equal to V itself, which I can write work done per test charge. So minus and plus we gets cancelled, so we can get the dV equal to work done per test charge. So here work done equal to dV times test charge. So here the work done is not equal to 0 when you move across. So here the dV is difference in the potential, small difference in the potential times test charge. Let me take as equation 1. And we know one more work formula. So work means nothing but the force times displacement, F dot ds. So here I will take that ds is as from here to there, so that I will mention in terms of the dr. So this small difference in the distance, so that I can take in terms of the dr. Now in the formula, if you can take that as F dot dr, so that's easy to write. Now here the force we can write in terms of the electric field. So the force what we mentioned here, the external force which is required, if you can write it here, the external force which required to move the test charge Q naught against the electric field. Electric field is given by the force and electric field relation, because force equal to minus E bar dot Q naught. So this how did we get? So if you can remember, what is the electric field formula? Electric field equal to force per test charge. Okay, so here the negative sign, why? Because we are doing the work opposite to the electric field. Now if this is the force, what you can write the displacement. So if you can write the work, so you can substitute that. Therefore the work done to move a test charge test charge Q naught from A to B is, if you can take the work formula, work equal to force times small displacement as dr. Now I can substitute the force value which I have at here. The force F equal to minus E bar dot Q naught. Therefore, I can get work equal to minus E bar dot Q naught. So this is the another work relation which I got with the help of the electric field. So let me take as equation 2. Now by equating 1 and 2, so from the first you can get work equal to dV times Q naught, and from second work equal to minus E bar dot Q naught. Therefore dV times Q naught equal to negative E bar dot Q naught. Now they both are the works times, sorry, here I need to substitute the value of dr. So here the displacement I do not substitute, so that will becomes dr. So minus E dot times Q naught times dr, that is the displacement. So this together will be get as the work. Force times displacement, I substitute only the force formula, so I need to substitute displacement 2 also. Now if you can cut the Q naught test charge gets cancelled. Now we can write the electric field E bar equal to negative of dV by dr. So this is the electric field and potential relation. Electric field E bar equal to negative dV by dr. So here we need to learn certain language. So that is here dV by dr we known as potential gradient. Potential gradient, strictly electric potential gradient. So what does it mean? Potential per unit length. Potential per unit length. So that we termed as potential gradient. So what is the negative sign represents it here? The negative sign represents the direction of electric field in such a direction where the potential gradient decreases. So the electric field direction in such a direction, so that direction is in which direction the potential gradient decreases. So how do you understand that? Now take a positive charge at here. Now if I take this is positive charge. Now if I can draw the electric field lines right now at here. Now this is the electric field line. So that is the electric field line's direction, I know it. Now if I can take 2 points at here. So now that point B and this is the point A. Now if you can write the potential difference VB minus VA. Now if you can take the VB minus VA value, you will get as negative, as minus. Why? Because so VB value is smaller than the VA. So here VB value is less than VA. Why it is? Because the distance, the B is farther than the A, since potential is inversely proportional to R. Potential is inversely proportional to R. Therefore, the distance from the R from A is small than the B. So potential will be B is lesser. Now the decrease in the potential, we can mention the decrease in the potential as VB minus VA. In the same the direction, the electric field is also represented. Now if you can see, the electric field is representing where the potential gradient decreases. Or if you can see in another angle also, if I move from A to B, so the potential value, what happens? Its value goes to decreases. So when you can move from the A to B, the potential value decreases. So that is shows the direction of the electric field. So here the negative sign represents the electric field is in the direction in which potential decreases at steepest. So that I can mention it here. Electric field is in that direction in which the potential decrease steepest. So finally, the relation between the electric field and the potential. Electric field and the potential, which we can mention as E bar equal to minus dV by dr. So here the dV by dr we are mentioning as potential gradient, which also known as potential per unit length. And the negative sign shows about the decrease in the potential. In that direction only the electric field represents. The electric field directions in such a direction where the potential decreases steepest.